Hello AP Physics students. In this video I'm going to show you how to solve a problem involving capacitors in series and parallel. And just like any other AP problem, you have to follow certain steps in order to get to the final answer. So let's take a look at this circuit. You'll see that there's two parallel capacitors, and those are in series with another capacitor. So the first step is always to find the equivalent capacitance of the entire arrangement of capacitors. And we can actually reduce these two to be one capacitor, like the two in parallel, right? There's a gap in between each of them, and they'll act like one kind of big capacitor, like the capacitance adds for capacitors in parallel, right? Cp equals C1 plus C2. So this capacitance is equal to 6 total microfarads for the two parallel capacitors. So then we can figure out, all right, that's in series with 3. So with series, right, it's this other formula, but you got 1 over 6 plus 1 over 3, and that's 1/2 actually. So see, the capacitance in series is 2 microfarads total. So if that's the total capacitance, we can now find the total charge. The total charge is just the total capacitance times the total potential difference across all that stuff. So the total charge is going to be 2 microfarads times 12 volts, 24 coulombs, microcoulombs. Where is that charge? Well, if you've got capacitors in series, right, that charge had to come from the other capacitor because there's like a gap in each capacitor. So there's 24 here, and then there's 24 over here. This would be negative in this case, right? And so there's like positive 24 on this plate, negative 24 on that plate, and that charge had to go from one plate to the other. That's why it has to be the same everywhere. So now that we know there's 24 on each plate, we can actually start to figure out the rest of this problem. So we know there's 24 here, 24 there. Now the step is to find how much potential is across each capacitor. What's the difference in potential for each one? Well, we can just use this handy dandy thing, right? Just simple relationship. So we got 24 over 6, 24 over 3. The potential across the parallel, which is the same for both, right? Got these key little things to remember on the bottom here, is 3 volts. Wait, 4 volts. And for here, it's 8 volts. Oh, hey, those add up to 12. That makes sense. So now we know how much potential is across each one. Well, wasn't this 4 volts across 6? But I guess that means you have each of these two in parallel there's like a 4 volt difference across each of those two, right? If we make a picture of the circuit, you might be able to see this a little bit better if we color code things. So this is the last step, right? Now we can finally determine the energy. There's basically a high potential all along here. On the left side, there's 12 volts, right? If we say 0 is the negative plate, and then it drops 4 volts to 8 volts here, and then on the right side, you're back to 0 volts, right? And there's a difference across the gap of each capacitor. And the two parallel ones share that difference of 4 volts. There's a couple different formulas for energy. Why don't we just use this one because we already know Q and V for each capacitor, right? There's 24. Oh wait, maybe we can use that for the 3 one because we know there's 24 microcoulombs times 8 volts of difference. So that's going to give us 96 joules. The other two, well, it might be easier to use this guy. So let's go with, because we know it's a difference of 4 volts. And then 2. And we find that it's 32 and 16. You do have to realize that, with capacitors, when they're in series, that the voltage has to drop like in order. It can't go all the way to 0 all across all, like they each have to share the same amount of charge. So each one has to have some difference in potential across each one. But if you follow all these steps, you will be able to solve any of these problems. They're just logic puzzles. Good luck.